Hello everyone, I hope you are doing well. So in this video, we are going to discuss Geeks for Geeks problem of the day, and today's problem is AVL tree insertion, and it is a hard level problem. So I believe this problem is not that hard. The only thing is, in order to solve this problem, you need to understand a lot of different concepts, right? And understanding those concepts is itself very hard. And once you have understood all of those concepts, then it is not very difficult. So the things that you need to know in order to solve this problem are, first of all, what is an AVL tree? So you must have heard of binary search trees, right? And it is similar to insertion in a binary search tree with a couple of extra steps, right? So AVL tree is also known as self-balancing binary search tree. Now, in order to understand what is self-balancing, you need to understand what is the difference between a balanced and a non-balanced binary search tree. Then you need to understand what is a balance factor. Then you need to understand how you can balance a binary search tree. What are the different kind of rotations? There are 4 different primary rotations: left, 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 right, 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 and right, left, right? So there are a lot of things to understand for this particular problem, and I already made a video on this problem itself. So it was on 31st August, the problem of the day for Geeks for Geeks. I have made a video. I'll try to leave a card on the top right somewhere around here, so that you can just click on it and watch that particular video, right? So that problem was about deletion in an AVL tree. So this problem is going to be very similar to that particular problem, and in fact this problem is easier than that particular problem. So how do we insert and delete in AVL tree? The first and the primary steps are very similar to the binary search tree, right? Just like how you insert in a binary search tree and how you delete in a binary search tree, you're going to follow the same steps. Now after you have inserted or deleted your desired node, you would want to balance the tree, and the steps for balancing is exactly the same for both insertion and deletion, right? So for this particular problem, I'm only going to discuss the differences in this problem and the deletion problem which we had, so that we can save some time, and I don't have to explain the same concepts twice, right? So I highly recommend you to watch that video first. If you want to watch, you could watch the starting part of the video where I have explained what is AVL trees, what are the different kind of rotations. You do not need to watch the deletion part, because this problem is going to be about insertion. But before the deletion part, you can watch everything, and once you understand all of those concepts and come back here, I'll try to explain what is the differences between this problem and that problem, right? So I believe now, if you have watched that video, you must already be familiar with all these kind of rotations that they have explained here. You must already be familiar with all the other things regarding the AVL tree as well. So now, assuming that you know all of these things, I'm going to explain this code that I have written, right? So first of all, this is my insert to AVL tree function, right? Now this part is very similar to what we generally have in a binary search tree. How do we insert a node in a binary search tree? We try to find the correct position for my desired data, right? So if data is less than node data, that means if data is less than the data of my current node, I'm going to insert the current data into the left subtree, right? Because it is a property of binary search tree that all the smaller values will go to the left, right? So I'm just marking node left is equals to insert into AVL. I'm recursively calling the same function, and I'm going to insert in the left subtree, and the data is the same. Similarly, for the right subtree, I'm going to pass node.right, and the data is the same. Now, if I have encountered a null pointer, that means I have encountered the correct position to insert the node. I'm going to create a new node with the desired data. So this is the default constructor, and I'm going to set the height of this particular node as 1. Now I'm going to return my new node. So till this part, this was simple insertion in a binary search tree. Now whatever code we have after it, this all code is for the balancing of the binary search tree, or to make it an AVL tree, right? So I believe this part, this starting from here, this part. So this is exactly the same code that I could have written there. It's just that I wrote it a couple of months back, so the implementation might look a little bit different, but the idea is the same. I'm trying to find out what kind of imbalance is present here, and based on that imbalance, I'm trying to balance the tree, right? So you can either follow that particular code or this particular code. There is no difference as such. It is both for balancing the trees. It's just that I have written this code right now. I did not take the same code, so that is why this code might look a little bit different. but I'm just quickly going to walk through what I've done here, right? Now, one more important difference that we had there was, in that particular problem, there was already a function called set heights, which was essentially setting the heights of the nodes, right? But now here I don't have any such function in the driver code. Earlier there was a function in that particular problem to calculate the heights of the different nodes, but here I'll have to calculate the heights in order to find the balance factor. So I have this little function he, right? And I also have this height map. So this height map is going to be an unordered map which is going to store the height of different nodes, right? Now I check whether if current pointer is null pointer, I am going to return 0. Otherwise, I am going to return the height of my current node as maximum of left node's height and the right node's height and add 1 to it, right? So this is how I can calculate the heights of different nodes. Now I can calculate my balance factor as height of left node minus height of right node. So you see, by calculating the heights, I am also saving it. Now the reason why I had to do this was I also tried, you see, I have a couple of wrong submissions. Most of them are related to TLE. So here in this particular code, I'm calculating the height directly, right? So I did not save it anywhere. So that is why it was giving me TLE, right? Now the second and the third TLEs were due to taking the wrong kind of map. So you see, I have taken a map here. That is why I'm getting TLE. But in the final implementation, I have taken an unordered map. Now, one more thing, that the difference is, you see here I'm updating my nodes every time, right? For every node, even if I don't change them, I was updating the heights. But here you will see I'm only updating it if I rebalance the tree in any case, right? So this problem, the time limit was very strict, so we will have to take care of all these things, right? Now, so what I do once I've calculated the balance factor, so if absolute of balance factor is greater than 1, that means there is some kind of imbalance, right? Now if balance factor is less than 1, that means it is negative, right? So I can also write less than 0 as well, so it does not matter here. So if it is less than 0, it is a right imbalance, because in that case this height of right subtree was greater, right? Now I'm trying to find out where the new data was inserted, and based according to that I'm trying to find out whether it is right left or right imbalance. So if data is less than node right data, that means, let me just draw it once. So this is my current node, this is the right of my current node, and if the data is somewhere in the left subtree, that means the new node was inserted somewhere here, right? It can be a big tree and this was inserted somewhere here, right? So that means it is going to be a right left imbalance, because the new node was inserted here. The imbalance would be caused by some node in the left subtree. So it is going to be a right and then left imbalance, right? So this is how I figure out this is right left imbalance and form the rotations accordingly. Similarly, in the other case, it is going to be right imbalance. And now when I come to this particular case, if data is less than node left data, it is going to be left imbalance. So let me just also discuss this. If data, so this is node, this is node, this is node left, and if it is on the left of it, here it is going to be left, but it is, if it is on the right of it, it is going to be left right. How it is left right? Because it is first of all a left rotation here, right? Now the new node was somewhere inserted here, and the imbalance was caused by this particular subtree. So this is a left right imbalance, right? So I make the adjustments accordingly, and only if I have made some adjustments, I am going to update the heights of my current node and its left and right node, right? So it is very important to update the heights, because if you have entered this particular if condition, that means you would have made some changes to the node structure, right? Once you have made the changes, it is also important to update the heights of those nodes, right? So how is this function called updating the height? You see, I am also saving the height of the current node here. So whenever I call this particular functions, it is also going to update the heights, right? So if I call it not here but here outside the if condition, it is going to give me TLE, right? So this is also one thing that you need to take care of, that you are only going to update the height when there is some change in the tree structure, right? And it is also only going to change whenever your tree is imbalanced, right? So after all of these things has been completed, you can just return the node. So again, this part was exactly similar to that problem. If you have watched the video, it is exactly same. It's just that my way of implementation might have changed over the time. So this code might look a little different, but the idea is still the same. And I've told you all the differences. The first difference is this is going to be an insertion, so you have to act accordingly. And the second thing is I have to calculate the height manually here. In the previous problem, the height set heights function was already there, right? So these are the only two differences. So let me just quickly submit this once more and let us see whether this works or not. So the only change I have made right now is this one, where I have written BF is less than 0, balance factor is less than 0. So you see it passes all the test cases and the solution is absolutely correct. I hope that you guys were able to understand the solution, and if you guys did, then consider dropping a like on this video and don't forget to share your thoughts in the comments, because your engagement with this video really helps the YouTube algorithm to understand that this video is actually helpful for you, and it will be able to reach much more people like you who want to keep solving new problems. So that is it for today. Till the next video drops, keep coding, stay safe, bye bye.